Hey everyone, and welcome. All right, today we're going to peel back the layers of reality itself to answer a question that seems super simple on the surface, but is actually one of the deepest in all of science. What really is a force? This is going to be a journey that takes us from the formulas you probably memorized in school to the very fabric of space-time itself. So let's just jump right in. So we're kicking things off by taking a closer look at maybe the most famous equation in all of physics. Yeah, F equals ma. It turns out Newton's second law has this beautiful, kind of sneaky paradox hiding in plain sight. So let's just ask the big question right out of the gate. What actually is a force? And if your gut reaction is, well, it's mass times acceleration, you're not wrong, but you're also kind of missing the whole story. Okay, so this really gets to the heart of the problem. If we say that a force is defined as the mass of an object times its acceleration, then the law F equals ma just becomes mass times acceleration equals mass times acceleration. You see the problem? It doesn't actually tell you anything new about how the universe works. It's just a circular definition, completely chasing its own tail. And that is the key insight, right? The real genius of F equals ma isn't the equation itself. It's that the law is a program. It's like a command telling us, go out into the world, find things that cause acceleration, and figure out their own unique properties. It's a recipe for discovery, telling us to look for the character of things like gravity, or friction, or electricity. This brings up a huge difference between the world of math and the world of physics. Mathematics can deal with perfect, abstract things like a geometric triangle. But the physical world, it's messy. Take that chair. What is it exactly? The atoms on its surface are constantly flying off, dirt is working its way into the paint, you literally can't define it with perfect mathematical precision. It's an approximation. And that, right there, is maybe the most beautiful secret in all of physics. Its goal isn't to find some final, exact truth. The real glory of science is the art of finding better and better approximations, models that get us closer and closer to understanding the wonderfully complicated machine that is nature. Okay, so with that in mind, let's peel back that first layer of reality. We're going to start with the forces we can see and feel, the useful but kind of dirty forces of engineering. And it turns out these everyday forces are actually just incredibly complex summaries of much deeper things going on. So for something like the drag on an airplane wing, we've got this handy rule of thumb that the force is roughly proportional to the velocity squared. Super useful. But it is absolutely not a fundamental law of nature. It's just a rough average of a bazillion chaotic collisions between air molecules in the wing. In fact, the more precisely you try to measure it, the less true that simple little law becomes. And it's the exact same story with something like friction. That classic formula you learned in school is great for building bridges or cars, but what's really going on when two things slide? It's not just little bumps grinding past each other. It's atoms literally grabbing onto each other, surfaces getting squished and deformed, and all that motion creating vibrations we feel as heat. It's a beautiful mess. And get this is one of my favorite facts in all of physics. If you take two chunks of pure copper into a vacuum and you clean them perfectly, perfectly, so that there's nothing but copper atoms on the surface, they don't slide. They stick. They fuse into a single block of copper. Why? Because the atoms have no idea they belong to separate chunks of metal anymore. So what we call friction in our daily lives is really the physics of dirt and oxides and all the other gunk on a surface. And that paradox, that's our big clue. To really get what's going on with these messy surface-level forces, we've got to zoom in. We need to look past the engineering approximations and see the atomic machinery that's actually running the whole show. Okay, this graph right here, this is basically the secret blueprint for why the world feels solid. At the atomic level, everything is a game of push and pull. See how the curve dips down? That means atoms attract each other when they're a little bit apart. But if you try to push them too close together, that curve shoots way up. That's a powerful, violent repulsion. That's why you don't fall through the floor. This dance of attraction and repulsion is the true origin of friction, of solidity, of pretty much everything we touch. So you might be wondering, how do we get a simple, clean rule like the one for a spring from that messy-looking curve? Well, think about it. If you only stretch or squeeze the atoms a tiny, tiny bit away from where they like to rest, right in the middle of that dip, and you zoom way in on just that little section, guess what? It looks almost perfectly straight. And that's Hooke's law for springs. It's a beautiful, simple approximation that emerges from a much deeper and more complicated reality. Okay, let's take a breath and put it all together. what we're seeing is a nested reality. On the very outside, we have those messy but useful engineering approximations, like friction and drag. We've seen that they arise from their atomic origins, this dance of intermolecular forces. But that just begs the next question, right? What governs the atoms themselves? And that question brings us to the deepest, most fundamental layer of all. We're leaving the approximations behind and looking for the elegant, fundamental forces. These are the simple blueprints that build all that complexity we just talked about. Now, one of the most powerful ideas here is the concept of a field. The old way of thinking was like spooky action at a distance, where the sun just magically pulls on the Earth across empty space. But the field view is much more elegant. It says a charge or a mass doesn't pull on another object. It changes the space around it. It creates a condition in space, a field. Then another object just responds to the field right where it is. It's a beautiful idea that solves a lot of problems. Okay, and now we're going to take a turn into the truly weird. You've all felt this, right? You hit the gas in your car and you feel thrown back in your seat. That force you feel? It's called a pseudo-force. There's nothing actually pushing you. It's a phantom force that appears simply because you are observing the world from an accelerating point of view. But here's the kicker. Here's the big clue. Pseudo-forces have a telltale sign. The force you feel is always perfectly proportional to your own mass. A bigger person feels a bigger push. Wait a minute, does that ring a bell? There's one other famous force that works exactly like that, and that's gravity. And that little clue, that's what led Einstein to arguably the greatest leap of imagination in human history. He asked, what if gravity isn't a force at all? What if it's a pseudo-force we feel because we're accelerating through a curved, four-dimensional space-time? Look at the diagram. The two paths start out parallel, but they end up meeting. They aren't being pulled together. They're just following the straightest possible path through a universe that is itself curved. Mind blown. And that brings us to the very edge of what we know. Deep inside the atom, we have the nuclear forces. They are unbelievably strong, but only over ridiculously tiny distances. They don't follow the nice, simple laws of gravity or electromagnetism. They just sort of turn on and then die off exponentially. We have equations that describe them, but honestly, they're a huge puzzle we're still trying to solve. Whew, okay, so let's zoom all the way back out and just appreciate the journey we've been on. We've gone from the simple feeling of friction all the way down to the fundamental curvature of space-time itself. And what have we found? We've ended up with this beautiful, layered picture of reality. Some things, like friction, are messy, complicated, but useful approximations. Others, like electromagnetism, seem to be elegant, fundamental laws. And then there are these other strange things, like pseudo-forces that are just artifacts of our own motion, or quantum mysteries like the strong force. Each one has its place in this incredible taxonomy. And this visual, I think, captures the whole idea perfectly. Science isn't about finding that one perfect final answer. It's about starting with the messy, pixelated, chaotic view of reality and slowly, patiently finding better and better approximations, getting a sharper and sharper picture of how it all works. The real beauty of it all is the journey itself. This constant process of refinement that lets us understand, predict, and just marvel at the machinery of nature. It's a pursuit that never truly ends. So the only question left is, what will the next layer reveal?